All right, good morning, guys. So in this recording, what I'm going to be doing is going through the worksheet from yesterday, the 25th. We are going to be scrolling through this digital document, just like in this recording that I'm going to post on YouTube, but I'll also have a image. I took a picture of my work. I'll post it probably to yesterday's posting and also to today's, just for convenience sake. Um, I don't have a printer at my apartment, so what I'm doing is I'm just kind of writing down all of the blanks. So I tried to keep my work organized, but I will also be referring to that image as I go through the answers. All right, so on this worksheet, there was a bunch of nice little directions. You read a little bit more about polyatomic ions, nothing new, but nice to be able to read it once more about those ATE, ITE endings. So let's go through these. The number one, first problem here, I think I'll go across. So ammonium is NH4 plus, acetate C2O3. What did I do there? C2H3O2 minus. I don't know why I wrote C2O3O2 on my worksheet. I'm gonna erase that. C2H3O2 minus. Must have been thinking about something else. Next, carbonate CO3 2 minus, dichromate Cr2O7 2 minus, hydroxide OH minus, nitrate NO3 minus, nitrite NO2 minus. Again, that ITE forming, I like to say it is itty bitty. So it has one less oxygen than our ATE form. And we just said that nitrate was NO3, so nitrite must be NO2. I also think I put these on here twice. My bad. There is a second nitrite down here. Maybe I'll change it to an iodate or something for next year's kids. All right, so next, sulfate, SO4 2 minus, phosphate, PO4 3 minus, permanganate, MnO4 minus, nitrite, again, it's still the same, NO2 minus, cyanide, Cn minus. Make sure with your cyanide that you are putting a capital N. Oftentimes I have students that will put a capital C lowercase n. So make sure capital C, capital N minus. Sulfite, SO3, 2 minus. We already talked about sulfate, which is SO4, 2 minus. So sulfite, itty bitty, loses one oxygen. That's why it's SO3, but the charge remains the same. Versus for hydrogen carbonate, I will always call hydrogen carbonate bicarbonate. The reason why I like to refer to it as bicarbonate, although you are completely correct if you prefer hydrogen carbonate, is because in practice for our binary nomenclature, and it's an ion, so it's only going to be ionic nomenclature, we're going to be looking for two things. So if I gave you, let's put something with it. Let's say I gave you sodium hydrogen carbonate. You would look at that nomenclature and say, there's three words in there. This is odd. It would be a little bit easier if I said to you sodium bicarbonate. And again, it's the same polyatomic ion, hydrogen carbonate or bicarbonate. This is HCO3 minus. The charge has changed. Carbonate is CO3 2 minus. Bicarbonate or hydrogen carbonate is HCO3 minus. So just a -1. All right. Let's see, moving right along here. Number 2, what is common about most of the names of polyatomic ions? Most of them end in ATE. Again, this is not always true. These questions 2, 3, and 4, I just want you to think about them. I don't think any of these questions would be something that I would ask on a quiz or a test. They're very vague. A lot of the endings do have that ATE, ITE ending. They also will have a root to them many of the time. So sulfate, sulfite, thinking about chlorate, chlorite, those types of, understanding that, oh, this is the chlorate polyatomic ion, and I can apply the rules that I know about ate, hypo, and per. Number 3, what element do most polyatomic ions have in their formula? This is oxygen. That's kind of what we're looking at here. We had a special term for these. This is just that first grouping, I should say, that table on your polyatomic ions. We call these the oxyanions. So because they have oxygen in them, their number of oxygens follows that ATE, ITE rule. We have a ton of other polyatomic ions that, of course, do not follow this rule. What type of elements are found in polyatomic ions, metals or nonmetals? Mostly nonmetals. However, there are a few exceptions. Dichromate, chromate, permanganate has some metals in there, the chromium and the manganese. All right, so moving right along here, the thing that I really wanted to get to today, and also give you guys a little bit of examples to look at when you look at the image of my work, is the naming practice. So in number 5, you're going from your formula to nomenclature. And in number 6, you're going from your nomenclature to formula. You are going to be expected to go either way to be able to go from formula to nomenclature or nomenclature to formula. You'll also have to do these within a problem. So right now we are learning, and as you'll see from today's work, we have a bunch of practice work that we're going to be able to do with nomenclature. Like I said in class, that kind of drill and kill. The more practice you do, the more comfortable you will be at doing it. But the reason for this is in the future, we'll have some questions, and you might get a problem that says, sodium chloride reacts with dihydrogen monoxide. How do you expect these two to react? We're going to have to understand, well, what exactly is the chemical formula of both of these things? So that's why nomenclature is important. So when we're looking at a formula here to determine the nomenclature, first and foremost, I'll say everything on this worksheet has a set charge. But when you're looking at something maybe outside of this worksheet, you need to be able to determine it. So for all of the examples in number 5, what you'll notice is the metal, whether it's sodium, barium, aluminum, calcium, zinc, all of these metals have a set charge. The other part to it, the anion part to it, all of them are polyatomic ions. So these look maybe bulky. They don't look like they just have two elements in them, like maybe sodium chloride does, our classic example. But because they both have set charges as a set charge metal and a set charge polyatomic ion, and again, there's no variance in here, they're always going to have the same formula that comes from those two ions. So for NaOH, there's one sodium and there's one hydroxide polyatomic ion. There could never be more than that to create this neutral ionic compound. So we are still sort of forced to create a working ionic compound. It has to be neutral overall. So for number 5, let's get through these answers. First one here, NaOH, this is sodium hydroxide. NaC2H3O2, sodium acetate. BaSO4, barium sulfate. AlPO4, this is one of my favorites. I used to have a license plate. I don't anymore, but I used to have a license plate that had this on this. Not like on purpose, but but anyways, this is aluminum phosphate. NaClO3, this is sodium chlorate. CaOH in parentheses 2, this is calcium hydroxide. I like this calcium hydroxide example, and it goes to show you, and we'll see it in number 6 when we get down to going from nomenclature back to formula. But for calcium hydroxide, we have 1 calcium and 2 hydroxides. The reason we have to have 2 hydroxides is because calcium is an alkali earth metal. It has a set charge of 2+. Hydroxide, as a polyatomic ion, has a set -1 charge. So we need 2 hydroxides. You don't have to say that in your formula. For example, when we practice covalent nomenclature, you will tell the reader about how many atoms. You never have to do that in ionic because, again, it will always be the same combination to make that neutral compound. Moving right along here, the next one, ZnCO3, that is zinc carbonate. AgNO3, that is silver nitrate. Last part here, number 6, and I think I'm doing okay on time. So this is the one that I have the most work on my image for. You guys should be looking at that. The process that I like to do is to write the ions above or nearby the name of whatever I'm looking at. So if you're looking at my image, you'll notice, and I think I use red and purple, that sodium, I write Na plus right above it. And nitrate, I write NO3 minus right above it. While you're doing this, again, I expect you guys, it would be fabulous if you have memorized your polyatomic ions, but feel free, have your polyatomic ion sheet to go and pull those polyatomic ions off of. So if you're saying, well, sodium is Na plus and nitrate is NO3 minus, because we have a positive one and a negative one, they cancel out just by having 1 atom of each. So that's why our formula is just NaNO3. When we keep going here, I think we'll see some change once we get to our third example. So let's do potassium acetate, and then we'll start talking about something different in our aluminum sulfate example. So for potassium acetate, potassium is a +1, acetate is a -1. You just list them. That's why it is KC2H3O2. All right, so the next one here, aluminum sulfate. So for aluminum sulfate, aluminum, and again, this is one of those newer set charges. Aluminum, zinc, and silver have a 3-2-1 set charge. So aluminum does have a set 3+ charge, although it is not an alkali or an alkali earth metal. Sulfate, SO4 2-. So is with a +3 cation and a -2 anion, our least common multiple, the way that we're going to be able to get to neutral or 0 on our number line, is with a 6 on either side. So we want to have enough atoms of aluminum to create a +6 and enough polyatomic ions of sulfate to create a -6. This is the crossing over idea. So if we recognize that with aluminum's 3+, we're going to need 2 of them. That's kind of like the 2 on sulfate's ion charge. And then if we look at sulfate and recognize that it's a 2-, and we need to get to a -6, we need 3 of them. That's kind of like the 3 charge on aluminum. So that's the crossing over idea. Again, some of you just have math brains and you're like, oh, I know 6 is the least common multiple. That's how I get there. But I always, always, always encourage you to write the ions out. It's super, super common that you will mistakenly give me something like Al3SO4 and parentheses 2, which would be pulling down your multiples or pulling down your charges instead. Okay, so be careful. Again, the correct formula, as you see it on my image here, Al2, parentheses, SO4, and parentheses 3. You can't distribute the 3 to your oxygen and sulfur inside your parentheses, so it could not be like Al2, S3, O12 or something like that, because what we're trying to say here is that's sulfate. It gets stuck together by itself. So another reason why we're memorizing these polyatomic ions, they're so common and so prevalent that we do have to memorize them, know their charges, and know that they act kind of like elements in that they're not going to break apart. All right, moving right along here, potassium dichromate. Potassium has a +1. Dichromate is a -2, so we need 2 potassiums. That's why it is K2Cr2O7. Ammonium sulfate over here, very similar. We need 2 ammoniums. Ammonium is a polyatomic ion. It is NH4+. It's the only positive one. So our formula for ammonium sulfate is going to read parentheses NH4 and parentheses 2 SO4. Last ones here, and I'll try and wrap this up. Lithium chlorate. These are equal but opposite charges. So lithium is a +1, chlorate is a -1. So it's just LiClO3. Magnesium nitrate. Magnesium does have a 2+ charge. Nitrate is only -1. So you need 2 nitrates. This should be Mg parentheses NO3 N parentheses 2. Next, ammonium acetate, my favorite. This ammonium acetate is my favorite polyatomic ions. I should say my two favorite polyatomic ions smushed together in an ionic compound. This one's my favorite because it is so crazy looking. It is an ionic compound even though it only has nonmetals inside of it, which is another reason why it's so interesting. But ammonium acetate, NH4C2H3O2. Sodium sulfate. We have a -2 charge on sulfate and a +1 on sodium, so that's why we need 2 atoms of it. It's Na2SO4. And lastly, our potassium nitrate, KNO3. All right, I'm going to do a couple more examples in your work for today. So if you would like any more, please let me know. I hope this helped. Let me know if you would like me to say a little bit more about anything, okay?